This is lecture 1, the part 2 for the introduction to systems engineering. And this is a continuation of our previous recorded lecture. In that lecture, we would define what systems engineering is. And we also compare systems engineering with other disciplines in engineering. We presented some examples of systems that requires systems engineering, and we clarify in terms of what are the differences, what type of systems and why those systems will require systems engineering. So today we're going to continue that discussion. And as always, I start my lecture by providing you with the references. So this lecture is using as a reference these two textbooks that are in red in this slide. So we start today's lecture with this quote in which Aristotle states that the whole is more than the sum of its parts. And this is clearly linked to what the goal of systems engineering. In order to achieve this goal, we need to be able to combine all these disciplines in the design of a solution for a particular project. And most of the time that requires different pieces that by themselves cannot solve the problem, but when you put them together through interfaces and through collaboration, they become a complex engineer system that is able to accomplish that goal. So in our lecture, we are going to look at these three areas that are highlighted. We're going to start with the systems engineer viewpoint. And as part of this piece, we are going to have a case study. So that's going to be linked to the first lab for this class. And then we're going to look at the systems engineering as a profession, and finally, the power of systems engineering. So what is the systems engineer point of view? Makes the central objective the system as a whole and the success of its mission. Okay, so we are mostly worried about that final goal. And we know that for us to be able to get to that point, there's a lot of things that needs to happen. We understand that. But our central objective is to accomplish that final mission. So we take a big picture approach or a holistic approach, which is a view of large scale problems and their proposed technological solutions. So we are basically looking for that balance that is going to, as you remember from our previous lecture, this is a complex endeavor that we are trying to achieve, but we want to find that perfect balance between schedule, cost, and performance. So we are looking for that balance system that is not just forcing the design to go on specific discipline or a specific viewpoint from the specialist point of view, but that is a system that is capable of taking all these disciplines and find a combination that is balanced and that is able to accomplish the mission. So the actual point of view of systems engineering is to find the best system. And I want to make a note here, because if you, for example, have taken operation research and optimization courses, when we are looking at the solution for those type of problems, we are looking for the optimal solution. So the optimal solution will be that solution that is the best among all possible solutions. That is not necessarily the point of view of systems engineering. We are looking for the best system, and the best is the name of the good. So systems engineers, we talk about systems engineering as the art of the good enough. Okay, so remember that three pillars: schedule, performance, and cost. So can we accomplish our goals by making sure that we are within the constraints for those three areas? So systems engineering seeks the best possible system, which often is not the one that provides the best performance. As I mentioned already, we are not looking for the optimal performance necessarily. We are looking for the best balance, because as I mentioned in our previous lecture, if sometimes for you to be able to get that best overall performance, maybe you need to wait a long period of time, and maybe you don't have that much time, or you don't have the resources to accomplish the cost, to cover the cost of getting to that performance level. So the best possible system within our constraints. Systems engineers or engineering views performance as only one of the several critical attributes. We also look for affordability, timely availability to the user, easy of maintenance, adherence to an agreed upon development schedule. So the systems engineer seeks the best balance of the critical attributes. So on the next slide, I'm going to show you a graph that is trying to show or represent or model the discussion that we just had. So in this graph, you have the performance level on that y-axis, and then you have also cost on the x-axis. And you see that there's a curve in this graph, and in that area where the curve is, there's also three dotted lines. Those three dotted lines are representing some performance levels. So the bottom one is 60%, the top one is 100%. And in between is what we consider our desired performance, which is between 80 and 90%. That 60% is our minimum acceptable level. So when you look at this curve, what we are trying to represent here is that there's an increasing cost as you move forward into that performance level, for instance, to the minimum acceptable level. So from Z0, you see that there's, in order for you to get to that 60%, you have to move toward the right in terms of the cost, and there's a cost associated with you achieving that minimum acceptable level. Same thing if you want to get to that desired level, you see that the cost is increased. So that is represented also with the curve. And the other thing is, as you go farther, or as you try to achieve that 100% level, you see that at some point the increase in performance is so small, but the cost is very large. So for example, when you get to 97%, even if you put more money or if you spend more money, there's not a major difference in terms of the increase in performance. So this is what we call the law of diminishing returns. So at some point, you're going to plateau, and it doesn't matter how much money you put into the project, you know that the performance is maybe possible for you to get that to 100%. The next graph is basically showing the same information from a different perspective. So now instead of performance, in the y-axis, we have a ratio of performance divided by the cost. So now we have a curve that has, is very easy to see what the maximum level is. And at some point, you're gonna get to the high point, and then there's no way that you go back to that high level, even if you spend more money. The graph is also showing the minimum acceptable performance and also the desired performance. So that ratio performance cost is telling you that you get to that minimum acceptable performance is almost at the top. That's basically representing your best ratio, but the performance is maybe not as good. So you can spend a little bit more money, but you know that that ratio is going to decrease. So it's up to the designer, and also in terms of the constraints that you have for the project, in terms of how much, in terms of budget, to decide where that point is. If you want to get to the desired performance, most likely you want to get there, but the cost is associated with you getting to that point. So looking at this, finding that balance for you as a designer or for your customer is very important. As I mentioned at the beginning of the semester, there's several case studies that I want you to study as part of this class. One of those case studies is going to be presented next. And this is the case study for the Hubble telescope. So there were some testing decisions. There were some costs associated with those testing decisions, and then those decisions were made, and there were problems with the performance of this telescope. So the story behind this was the University of Princeton University in 1946 suggested that a telescope in space will eliminate the atmospheric effects that blur images seen on Earth. So the National Academy of Sciences proposed launching a telescope into space in 1972. So NASA began the Hubble Space Telescope in 1977. The Hubble was ready to be launched in 1986. And in April 1990, the Hubble was launched on May 20th, which was the moment of truth. Basically, at that point, that's after all these years of development of this system, a new system, a complex system, an engineered system. After this, I don't know how many years, about 28 years of development from proposal to launching, you get the moment of truth in terms of seeing whether or not this is going to perform as expected. And a lot of money went into this system. So what I want you to do is you're going to answer these questions that are here in slide 11 as part of your first lab. What was the goal of the Hubble? What was the overall estimate cost of the project? And what was the problem with the Hubble? And question number 4, how could this problem have been avoided? Do you think the cost for preventing the problem was justified? So how are you going to answer this question? So I'm going to, if you go to Canvas, you will have access to this document. So in this document, you're going to read it. It's short. There's some figures in it, and you're going to find the answer to those questions. Okay, and I want you to keep in mind, like if you were the systems engineer in charge of this mission, how would you approach some of the decisions that were made? Would you make them different, or would you follow the approach that they follow with the information that they had on hand at that time? Okay, so that's going to be your first lab. And again, you're going to upload these answers for questions, the answer for these 4 questions. They could be short, 1 sentence per question. You don't have to write a lot. But in the assignments, you will find the link to upload and the deadline. to upload the answers for these questions. Okay, so let's continue. So this next slide is going to discuss systems engineering as a profession. So unfortunately, systems engineer as a profession has not been widely recognized despite of increasing prevalence of complex systems. Is the essential role of systems engineering in the development of systems. So the systems engineering primary recognition has come in companies specializing in the development of large systems, mostly military companies, DoD contractors, NASA, Boeing, all these companies that are in charge of keeping the nation safe, and also those companies that are doing science at the large scale. Those are companies that requires the skills of a systems engineer. Perhaps the main reason for the slowness in recognition of systems engineers as a career is the fact that it does not correspond to the traditional academic engineer disciplines. Engineering disciplines are built on quantitative relationships, obeying established physical laws, measure properties of physical material, energy, or information. Systems engineer, on the other hand, deals mainly with problems for which there is incomplete information, whose variables do not obey known equations, and where balance must be made among conflicting objectives involving incommensurate attributes. The establishment of systems engineering as a unique discipline has been inhibited by the absence of a quantitative knowledge base. Despite those obstacles, the recognized need for systems engineering in the industry and government has spurred the establishment of a number of academic programs offering master's degrees in systems engineering, mainly as components of part-time continuing education. A few universities are offering now undergraduate degrees in systems engineering as well. There has also been relatively recent recognition of systems engineering as a profession in the formation of a professional society, which is the International Council of Systems Engineering, or INCOSE. One of whose primary objectives is the promotion of systems engineering education and the recognition of systems engineering as a professional career. So in terms of the orientation of technical professionals, scientists are typically dedicated to understanding the nature and behavior of physical work. They typically ask these questions: why and how? A mathematician primarily concerned with deriving the logical consequences of a set of assumptions, which may be unrelated to the physical world. For example, develops the proposition, if A, then B, and they show a proof of what's going to happen. An engineer usually is concerned with creating a useful product. Okay, so we can say that from a systems engineering perspective, you have a little bit of each. So that's what we are trying to showcase here in terms of the orientation of systems engineering. So you will have, as I mentioned in this triangle, we're trying to measure the percentage of mathematics, percentage of science, the percentage of engineering. So it's going to be, as you can see here, from a mathematic perspective, going to be in the 20s. From an engineering perspective, you're going to be in the 80s. And then in science, you'll be between 60 and 80. And you can see now that that triangle right there in the middle, that black triangle, is showing technical orientation, population density distribution. So you can notice the, I'm sorry, let's go back, difference of those two triangles, right? So if you look at the overall density distribution of the population, that triangle is a little bit higher when compared to typical orientation of systems engineering. So that makes it difficult also for the discipline to recruit, let's say, and also to have the people with the mindset required for this type of profession. So systems engineering represents, and that's the challenge of systems engineering. Systems engineering represents a deviation from a chosen established disciplines to a more diverse, complicated, and uncertain professional practice. Requires investment of time and effort to an extensive broadening of the engineering base, learning communication and management skills, a much different orientation from the individual's original professional choice. So one may conclude that a career in systems engineering is a difficult road, not obviously rewarding, and altogether not very attractive. For the systems engineer, success is measured by the apparent absence of program difficulties, rather than by spectacular successes. So what we're trying to say in this slide is like, if you don't have the right mindset, if you cannot see things from a major, let's say, perspective, overall perspective, and see how things are linked in order to get to that final objective or your mission, then the career might be not as exciting as other careers in engineering. But it's a rewarding career. It gives you a different perspective of for solving problems. And for me particularly, this is one of the best courses and disciplines that I was able to study when I was a graduate student. So for me, systems engineering is a very interesting field that helps us in the problem solving problems. So the challenge of systems engineering, why do very good people devote their lives to systems engineering? The answer may lie in the challenges of systems engineering rather than its indirect rewards. So systems engineering deals with the most important issues in the systems development process. They do not design the components, but do design the overall system architecture and the technical approach. They prioritize the system requirements in conjunction with the customer to ensure that the different system attributes are appropriately weighted when balancing the various technical efforts. They decide which risks are worth undertaking and which are not, and how the former should be edged to ensure program success. It is the systems engineers who map out the course of the development program that prescribe the type and timing of tests and simulation to be performed along the way. So as we move forward in the design, then the systems engineer is in charge of making sure that as we do the experimentation, how likely are those experiments representing the actual performance of the future system. They are the ultimate authorities on how the system performance and the system affordability goals may be achieved at the same time. And when unanticipated problems arise in the development program, it is the systems engineer who decide who they may be solved. So systems engineers derive their ability to guide the system development, not from their position in the organization, but from their superior knowledge of the system as a whole, its operational objectives, how all parts work together, all the technical factors that go into its development, and proven experience in steering complex programs through a maze of difficulties to a successful conclusion. So next, we have a short discussion on the power of systems engineering. So the power of systems engineering, they have a great influence over the design of the system, the major characteristics, and the success or failure of the system development process. The influence comes from the systems knowledge, systems engineer knowledge, skills, and attitude. So in terms of knowledge, it has to be multidisciplinary. So you get these all come from experience. So as you start working together with all these different disciplines and you get exposed to what they do, then you get that multidisciplinary knowledge that is going to make you a very good systems engineer. Approximate calculation. So you are you have the ability to predict, somehow forecast what could happen if you go in one direction or the other. And the skeptical positive thinking, which is needed. Like you're gonna face some major challenges. So if you give up, then the whole thing will give up, and that's not an option. So you have to keep this positive thinking as you move forward with the project, and finding ways of making sure that you are able to move forward, even if you are presented with challenges. Multidisciplinary knowledge. A successful system requires specialists in different disciplines, and each specialist has its own language foreign to non-specialists, and also they have their own knowledge base. So systems engineers provide the linkage that enable these disparate groups to function as a team. Approximate calculation. Systems engineering requires the ability to make approximate calculations to ensure that a critical omission or error has not been committed. Based on past experience, yeah, definitely. Some of the things that you're gonna learn as you are exposed to more projects. Use first principles. Apply basic relationships, and examine basic assumptions and conditions. In terms of this skeptical positive thinking, skepticism is important to temper the traditional optimism of the design specialist. Probability of success of a chosen design, insistence of validation of the approach selected at the earliest possible opportunity. So positive thinking is important, but you also have to make sure that you do the right testing. You look at the design and you look at the technology. Is that something that, with your experience, are you able to say, okay, this is something that can work? Validation. If there's some new technology, make sure that you test, that you model, that you measure, and make sure that the performance is what you're expecting. You move forward only after validating those approaches. Positive thinking is necessary in reacting to failure, apparent failure of a selected technique or design approach. Many design specialists who encounter failure are plunged into despair. So the systems engineer cannot afford to be in despair. They need to find ways to circumvent the cause of the failure. Okay, so this is the final slide for this part 2 of the first lecture. Remember that you have a lab that you have to read and answer some questions. And I want you to pay attention to the decisions that were made on that case study and think about if you as an engineer will act in the same way or not if you were faced by a similar situation when you start your professional career. So thank you for watching, and we will talk again on the next lecture.